Welcome to EDU World Space.
So for our system of three particles, as in the previous problem, we can write down the position vectors for each of the particles. For particle A, Ra is simply 3 along the unit vector j. The position vector for B, Rb, is equal to 1.2 along the I direction plus 2.4 along j plus 3 along k. And the position vector of C relative to the origin is 3.6 I. So here we have our position vectors for our three particles. For part A of the question, we need to find the mass center of the system. And we know that the mass center is defined as follows. The masses of the three particles, Ma plus Mb plus Mc, essentially the mass of the whole system, multiplied by the mass center R, is equal to the sum of the product of the masses and the position vectors. So MA-RA plus MB-RB plus MC-RC. So since we know the masses, we get that 9 times the mass center R is equal to 3 into 3J, so the scalar product of the mass and the position vectors, plus 2, which is the mass of B, into 1.2I plus 2.4J plus 3K, plus the mass of C, which is 4 kg, into its position vector 3.6I. And from here, we can find that the mass center R is equal to 1.867, and that's in meters in SI units in the I direction, plus 1.533 meters in the J direction, plus 0.667 meters in the K direction. So that is our mass center of our system of particles. So that's what we need to calculate in part A. Now in part B, we need the linear momentum of the system. So we need to first calculate the linear momentum for each particle. Once we have the linear momentum for each particle, we can calculate the linear momentum for the system. So for each particle, the linear momentum is its mass times its velocity vector. And the velocity vectors are given, so it's simply again a scalar product. So the linear momentum for particle A is MAVA, and we get 12I plus 6J plus 6K. The linear momentum for particle B is MBVB, again a scalar product, gives us 8I plus 6J. For particle C, the linear momentum is MCVC, and this is minus 8I plus 16J plus 8K. And hence we have our linear momentum for each particle. Now that we have the linear momentum for each particle, we can calculate the linear momentum of the system. The linear momentum of the system is the mass of the system, m, multiplied by the velocity for the system. And this is MAVA, so the sum of the linear momentum for each particle, plus MBVB. So MAVA plus MBVB plus MCVC gives us the linear momentum of the entire system. And we get the linear momentum to be 12 kg meter per second I plus 28 kg meter per second J plus 14 kg meter per second K. And that's the linear momentum of the entire system. Now, in order for us to calculate the angular momentum about the mass center, we need to calculate the position vectors relative to the mass center. So the position vectors we have the position vectors relative to the origin. We need the position vectors relative to the mass center G. And these again are in meters. So we'll call the position vector of A relative to the mass center RA prime. And this is equal to the vector RA minus the mass center R bar. And so doing this subtraction, we get 1 minus 1.86667 times I, keeping as many decimal points as we can for accuracy, plus 1.46667 J plus, or actually minus 0.66667 in the K direction. So now we do the same thing to find RB prime. That again is RB minus R bar. And this is minus 0.4667 in the I direction plus 0.8667 J plus 2.3 recurring times unit vector K. RC prime again is vector RC from the origin minus the mass center R bar, and we get 1.73333 I minus 1.53333 J minus 0.6667 times K. So we've kept all the decimal points for accuracy. And doing that helps us find the angular momentum about G. So the angular momentum is represented by H, capital H. And we want the angular momentum of the system about its mass center, point G. And this is defined as RA prime crossed with the linear momentum, which is MA VA for each particle. So that's plus RB prime crossed with its linear momentum, MB VB, plus finally for the last particle, RC prime crossed with MC VC. So the angular momentum is the position vector crossed with the linear momentum, R cross P. And so if we set up using the method of cofactors and we perform the cross product, we get that RA prime cross MAVA is 12.8 I plus 3.2 J minus 28.8 K plus the cross product for the particle B minus 14I plus 18.6667 J minus 10.933 K plus the final cross product gives us minus 1.6I minus 8.5 and 4 threes J plus 15.4667 K. So if we add all the like terms, we get that our angular momentum about the center of mass, hg, is equal to minus 2.8 kg meter squared per second times the basis vector I plus 13.33 kg meter squared per second times the unit vector j minus 24.3 kg meter squared per second times the unit vector k. So hence we have our angular momentum about the mass center of the system of the particles. Now, from here, we're going to prove that this matches our equation as required. So firstly, let's look at the vector of the mass center, the position vector of the mass center r bar, and we'll cross that with the momentum of the system, mv bar. And this is equal to, again, using the method of cofactors, I, j, and k, (1.86667) J is 1.53333 and K is 0.66667, crossed with the momentum of the system, 12, 28 in the J direction, and 14. So if we solve this cross product, we get this to be 2.8 kg meter squared per second in the I direction minus 18.1333 kg meter squared per second in the J direction plus 33.8667 kg meter squared per second in the K direction. So if we take our vector, our angular momentum h about the mass center g, and we add this vector r bar cross m v bar, we get minus 4.8 kg meter squared per second along the j direction plus 9.6 kg meter squared per second along the k direction. So that's our vector hg plus r cross mv. So the i's cancel. We don't have any component along the I direction. Now, if we find our angular momentum about O, HO is equal to RA crossed with the linear momentum of particle AMA VA plus the same for particle B, RB, where these position vectors RA, RB, and RC are the position vectors relative to the origin, and plus RC crossed with the linear momentum of particle C, MC, VC. So again, if we use the method of cofactors and we solve for the angular momentum about the origin, HO, we get minus 4.8 kg meter squared per second along the J direction plus 9.6 kg meter squared per second multiplied by the basis vector k. But look at these two values. So HO and HG plus R bar cross MV bar are the same. And therefore, as required, we can see that the angular momentum about the origin, HO, is equal to the angular momentum about the mass center, HG, plus the cross product of the center of mass, R, and the center of momentum, MV bar.